In this section, we'll be looking at some of the techniques used to graph polynomials, though because we're online for the semester, we'll be using Desmos quite a bit for this. So this is just giving you some general background information of how you would graph a function if you were doing it in paper pencil without a graphing tool to assist you. In the last section, we were talking about the number of zeros that you'll have for a polynomial, and we said that it's going to have at most n x-intercepts, n being the highest power of the polynomial. And then we have this new idea of what's called a turning point. A turning point is a relative maximum or minimum. So let's look at maybe something that's raised to the third power. Let's look at maybe x to the third power plus some other thing. I don't even know what this graph looks like. I'm just giving you like a general idea. I know that this graph is going to look like this in general. The zeros and everything are probably off, but just the idea is that because it's x to the third power, as x is going to as x goes to negative infinity, y goes to negative infinity. That's the end behavior. And as x goes to positive infinity, y goes to positive infinity, right? Because we're raised to the third power, there should be 3 zeros, 1, 2, 3. And then the turning points are going to be where the graph changes from increasing to decreasing or decreasing to increasing. And we would call that a relative, in this case, minimum. It acts like a minimum just in region of the graph, whereas this one is a relative maximum. Those are called turning points, and there are at most n minus 1. So n is 3. In this case, we have 2 turning points. So it's 1 less than the degree. Now, depending on how the graph looks, it might not end up looking that way. It might be that there are fewer than that, but that's the most that we could have. Here are the steps to graph a polynomial. We use the leading term to determine the end behavior. What's happening way at these extremes of the graph? Is the graph going up to positive infinity, or is it going down to negative infinity? We solve the equation, we set it equal to 0 to find the zeros, or x-intercepts, right? And then we can use those x-intercepts to break the graph up into smaller sections, and we can analyze what's happening in between the areas where the graph crosses or touches the x-axis. Is the graph above the x-axis, or is the graph below the x-axis? Plugging in 0 for x gives us the y-intercept. Again, that'll end up being that last term, the constant term on the polynomial. And then, again, if we were doing this by hand, we might want to put a couple additional points on the graph just to get a smooth graph. Depending on what we have, we want to make sure that we have enough to get a graph that makes sense. So here's a quick example. We have something that's raised to the third power. And so we know that the end behavior is going to look like this. The 2 that's in front is positive, so the end behavior is going to follow a standard x cubed graph. Setting that equation equal to 0, we factor by grouping, and we end up with 3 factors here, which leads to the 3 zeros or the 3 x-intercepts. This is all stuff that we've done before. The part that's new is to take those x-intercepts and break the x-axis up into 4 intervals. So this first interval is going to be from negative infinity up to the first 0. And then the second interval is going to be in between those 2 zeros, and so forth, right? We're just breaking this up into 4 different sections because we know that the graph is going to be sitting on or touching the x-axis at the red points, but we want to know what's happening with the graph in the rest of the areas. So what we do is we pick a test value for each point that is in that region. So the test value that we've chosen here is -3. It has to be something that's in this space, right? In between negative infinity and -2. So we just pick something that's just to the left of -2. Plug it into the original function, and the output they got is -25. So we know that the graph here is going to be below the x-axis. Following that same strategy for the next set, this is the next section, we plug in a value that's in between -2 and -0.5. They plugged in -1, and they got a positive value. So there the graph is going to be above the x-axis. Continuing, we're going to be below here, and then we're going to be above here, right? I'm just getting a general idea of what's happening with the graph, and so I think, well, this kind of makes sense if I connect these together, and that matches also with that end behavior idea that I had. We know that the y-intercept was -4, so kind of putting the x-intercepts together with the y-intercept and then maybe plugging in a few additional points to kind of figure out where this relative max and relative min are. This is the process we would go through to find a rough sketch of a graph. Here's a second example. This one's raised to the 4th power. So the end behavior is different for this graph. Because it's a positive x to the 4th power, both ends of the graph are going to be going up to positive infinity. Here's the factored version, and you can see that we have a multiplicity. We have 4 zeros, but this one is repeated twice. So breaking this up now into 4 intervals, using the zeros as the cut points for each of the intervals, we plug in test values. And the test values are telling us that they switched the table. The other table was going left to right. This one's going down. So here's each of the intervals on the top. This is the x value that they plugged in. This is the y value that they're getting as output. So for this first section, we're going to be above the x-axis because we're getting a positive value. Then we're below the x-axis, and then we're below the x-axis again, and then we're above. That tells me that right here at this 0, the graph is going to sit on the x-axis and not go through the x-axis because both sides of the graph on the left and right are both below the x-axis. So let's look at what the graph looks like. Yeah, so we can see here, this is where the multiplicity is, right, where we had something that was raised to the 2nd power. So you can see that this part of the graph looks like a parabola because that factor is raised to the 2nd power. And then the other ones that are raised to the 1st power with an odd exponent, the graph will go through the x-axis. Those are these two right here. This is a theorem that we use, it's kind of obvious when you learn what it is. We use it, again, for graphing. Don't stress too much about this because we're using Desmos, and so we're able to get a picture of a graph really easily. But this is saying something that's very obvious. It's saying that if I plug in 2 points and the signs of their output, their x value and their y value, one is positive and one is negative. Let's say I plug in A here and B here. And when I look at the output value for A, if one of them is up here and the output value for B is here, and I'm looking at a polynomial which is a smooth graph, it's just telling me that there has to be a 0 in between A and B. That if one of the values is positive and one of the values is negative, that the graph has to cross the x-axis at some time. That's all that it's saying. So we have a couple of examples here. In the first example, we have a function x cubed plus x squared minus 6x. And we're looking at these two values. We're looking at a is -4 and b is -2. And when I plug in the first one, I get -24. And when I plug in the second one, I get +8. So when I plugged in -4, I'm getting a value down here. And when I plug in -2, I'm getting a value up here. So my conclusion is, okay, well, there's got to be a 0 somewhere in the middle of these. This is a process that we would use to find the zeros easily when we didn't have access to calculators, and we would sort of hone in on, I know that the zeros have to be between these two values. And those of you that have used graphing calculators like a TI-89, that's the process you use on those kind of calculators. In the second example, we're plugging in -1 and we're plugging in 3. Well, when I plug in -1, I'm getting a value up here which is positive. And when I plug in 3, I'm also getting a value that's positive. The intermediate value theorem only works if you have a change in sign from positive to negative or from negative to positive. In this case, because both of the output values are positive, we can't make a determination. And looking at the graph, we can see, yeah, there are zeros here in the middle, and we can't conclude that there are not going to be zeros because we don't have enough information. So the intermediate value theorem only works when there's a change in sign in the values that you've chosen. All right, that's all for this video. I will see you in class. Have a great weekend.